Notice in the word electrostatics, there is the root electro, which is for electricity, right? And static is a fancy word. Static just means not moving, okay? So we're going to start off our study of electricity by looking at charges that don't move. And the reason why is it's simpler. And then we move into the fun stuff, which is electrodynamics, electric current, when you move a charge, okay? So electrostatics just means the study of electricity at rest, okay? The basic idea is you don't have to buy electricity. It just is part of nature. Electrons are electrically attracted to protons inside the nucleus of an atom, but repelled by other electrons. And much of chemistry is just understanding those electrical interactions and chemical bonding, etc. Okay? In terms of atoms, like we talked about, there's three basic particles. You have the electron, the proton, and the neutron. And they're actually named after electrical charge, right? Neutron is neutral, proton is positive, electron is negative. Helium is a great atom to draw out because it shows all the particles. Okay? Hydrogen is only a proton and electron, but helium, you have two protons. To keep the two protons from pushing apart, you put in two neutrons, which exert a strong nuclear force to hold it together. And then you have two electrons on the outside. And because of that, what's the net charge? Positive 2, negative 2? A big fat 0, right? So that's why when you touch a balloon, you're not like, ah, getting shocked there, right? It's electrically neutral. Okay? Now, a couple things about atoms, because it's actually important to understand the atomic structure there. If you remember from your chemistry class, the proton compared to the electron is huge. It's about 1,800 times more massive, bigger there. But the charge is the same. That's kind of weird, and that's just part of nature. So let me try to help you guys visualize that. So if you look at this balloon, let's say it's the proton.
And then I take this Post-it and I tear off a little tiny speck here. This could be like the electron. Okay? So ironically, the proton, even though it's like 1,800 times bigger, they actually have the same electrical charge. They'll balance out. Here's another thing that's weird. The nucleus is in the center of the atom. Okay? And so here's what's kind of weird. You can think of the nucleus like this, this balloon on the pitcher's mound in Wrigley Field there. And then we take this little, this little spit wad here, and we take it up to the cheap seats, the bleachers in Wrigley, right? And they go, we fling it, and it goes flying around the outermost part of Wrigley there, yeah? And then in between, what's most of the atom there? It's what? It's nothing, okay? It's actually not air, because air is made of atomic elements, nitrogen, hydrogen, oxygen. It's actually empty space. So atoms are mostly empty space. Isn't that weird? So you normally don't notice that because atoms have no net charge, so you don't get shocked. And then also, you don't notice an empty space because, well, I don't know. Let's think about it, okay? True or false, you have atoms in your knuckles. The answer is what? The answer is true, okay? You're actually mostly like carbon, nitrogen, oxygen, whatever. You're an organic substance, but whatever, right? The electrons and protons in your body are there. You just don't notice that, okay? Next, true or false? There we go. The next lunch bell. Yay. The table. The table is also made out of atoms. True or false? True. Okay, so if you're made out of atoms, your table's made out of atoms, and atoms are like 99.99% empty space. How come when you're knocking on the table with your knuckles, there we go, it doesn't feel like it's empty space? It feels solid. I don't get it. Or how come you're like knocking on the table and all of a sudden, shoom, your hand like passes through? Wouldn't that be weird? The table like, ah! Or you're kicking the table, right? And if your toe is mostly empty space, and so is the cabinet here, why not, shoom, your foot goes through the cabinet, or your foot gets stuck? Wouldn't that be weird? Okay, so why not? I don't get it. Well, what's on the outside of all your atoms? The what? The little tiny electrons, right? And do electrons like electrons? They don't. They what? They repel each other. Exactly. Okay? So you don't notice that an atom is mostly empty space because the electrons repel each other. So technically then, it feels solid because of the nerve endings in your body and all that. But actually, you actually never touch the table. That's actually kind of weird. Technically speaking, if you could zoom in with the world's most, actually, you know what? The world's most powerful microscope wouldn't work because it's smaller than light itself. But if you could zoom in and see it, your electrons in your knuckles come infinitesimally close to the electrons in the table, and they repel each other. Here's another way to look at it. You're not actually sitting on your chair. Isn't that weird? The electrons in your rear end are repelling the electrons in your chair, and you're just hovering there. Isn't that crazy? Okay? So
You guys don't seem that bothered because you're probably a little bit tired. It's right after lunch. But one year I had a group of swimmers, and they were really bothered by that idea that you never touch anything. Like, no way, that doesn't make sense. Like, when I jump in the pool, like, I don't touch the water. And I'm like, actually, you don't. They're like, what? Then how come you get wet? That doesn't make any sense. And what it is technically the water molecules will come infinitesimally close to your skin, and there'll be an intermolecular attraction there. But technically, they don't actually touch. It's kind of weird there. But for all practical purposes, on a macroscopic scale, of course you touch things. Okay? It's so small that the distance that they repel, you actually can't even see because it's smaller than light itself. Okay? And how would you feel things? Like it feels like you feel the table, or water feels cold, or whatever. Well, again, it's electrical interactions. When the electrons in the table repel the electrons in your knuckles, you might get a little pain sensation if you hit it hard enough, right? Or a cold sensation from the water. So, remember how it's all about seeing things you can't see? I'm going to try to show you guys a little simple demonstration. I'm going to do it tomorrow here. And I wish I could project this bigger, but I can't. That's okay. So tomorrow you're going to try this thing right here. It's very exciting. Wow. Okay, it's called a pith ball. Okay? And it's not because I have a lift, but a pith ball was traditionally made out of a plant material called pith. That's all. And they coat it with graphite. The same thing on your pencil. Okay? Nowadays, looks what we try to use is like styrofoam because it's lighter. Okay? And again, you can't see electricity directly, but you can see its effects, okay? So again, can you make electricity out of nothing? You can't, right? So what I'm doing is I'm separating the charges here, and the fur likes to lose electrons. The plastic likes to grab it. What do you know about opposites? They like to what? They like to attract. So if you look closer there, you can actually see the fur being attracted to the plastic pipe there. So if I got a little piece of fur on the table, Levioso, the little Harry Potter magic there, right? Okay? And that's because Mr. Lau joined Slytherin. I sold my soul to the devil. 666. No, just kidding, okay? No, okay? It's not magic. It's just basic science there, okay? Next, the pith ball. Okay, if you think about it, the pith ball, I can attract the positive charges in there with the extra electrons. So I can first attract the pith ball. There we go. Once I attract it, I can then add on extra electrons to it. There we go. Except it got tangled. Let me untangle there. And then do electrons like electrons? No. They don't. They're going to repel each other. You see that? So even though I can't see the charges directly, I can indirectly see their effects. Okay? You're saying, whoa, that's totally lame. Actually, it's really cool there. Okay? In real life, we take advantage of this. How? In all sorts of electronics. So this could represent an electric charge inside a memory chip, like for your digital camera. That's how you store your pictures. The Amazon Kindle with the cool electronic ink screen. You charge up a piece of electronic ink and you get it to stick to the screen. Xerox machine, you charge up toner, etc., etc. Pretty neat, right? Okay. So I'm going to show you guys now a little video clip that represents this idea of the size of an atom and the fact that you actually don't really touch anything. Okay. So this is Professor Krauss and another famous dude at Cambridge University, if you've been to the UK, to visualize this. Next, okay, big idea called the conservation of charge. In chemistry, you learn this thing called the conservation of mass, right? That matter cannot be created or destroyed there. So in a chemical reaction, the amount of mass before is the amount of mass afterwards. Well, another big idea is this idea of conservation of charge. You don't make electricity out of nothing, okay? You can't just generate electricity out of nothing. The English language, we say it wrong. You generate electricity or static electricity. What you're doing is you transfer charges from one thing to another. Okay? So again, back to rubbing the plastic stick on the fur there. Okay? That's called charging by friction. That's the easiest way to generate electrostatic charge, to see it there. So if you drag your shoe across the carpet, etc. there. Okay? So again, you're not making charge. You're just transferring it from one object to another. Next, in our notes here, you looked at this thing called Coulomb's law. It's a lot of weird math, but really what I want you to get is the big idea. Okay? We'll do a little bit of the math, a little plug and chug, but the big idea is more what counts. Okay? Charles Coulomb was a French physicist in the 1700s. He came up with the basic law of electrostatics, and that is the amount of electrical force between two objects just depends on the amount of charge between the two and then the distance. In honor of him, we named the unit of charge after him, the coulomb, which is capital C. And we were hoping that the coulomb could just be the charge of an electron, but it turns out we were wrong. The electron is really small. It's 1.6 times 10 to the negative 19th coulombs. It's a really small number, and it was hard to measure. And the guy who did it won the Nobel Prize, one of our first American Nobel Prizes. And it was actually a guy here at the University of Chicago. His name was Robert Millikan. Little physics, history, drama. After he died, turns out he was actually a real jerk. So the graduate students that had to slave away and work for him, they all hated on him after he died because he didn't really give them credit for their work, stole out of their ideas, that kind of thing. So a little physics drama, okay? But the big idea is, okay, that when you have two charges, they'll either attract or repel, and it only depends on the amount of charge present and the distance, okay? So up here is a really dramatic way to see this here, okay, in action. Okay, so I got a fun little toy here. It's called a fun fly stick, okay? And the way it works is when I push this button, there's an electrostatic generator in here. And it basically probably has like a felt roller. It spins, and then it rubs against a plastic roller. So then the felt furry thing gives away electrons, and then the plastic grabs it. Then I got a little piece of mylar foil. It's just a very thin plastic coated with metal to grab charge. Okay? And what do you know about electrons? Do electrons like electrons? They don't. So when I charge this up, the electrons pile on here. So it's kind of like you go out to college and you're in a dorm room with 6 people. And suddenly they open up an executive freshman suite and they say, hey, you get first dibs. Do you want that room? And you say, heck yeah, right? So the electrons don't like each other. They repel. They get onto the mylar there. And if you look closely here, isn't that cool? Okay? Mr. Lau can defy the entire Earth's gravitational pull with just a couple million electrons. That's all. But the point of this is electrostatic forces are very strong. They're super strong. Okay? They're billions of times stronger than gravity. You just don't normally notice that because your atoms stay together. You take that for granted. And also, okay, that normally things are electrically neutral. Isn't that cool? Okay, so you see that? So the electrons repel each other. That's why this thing is floating. And then if I put my hand out here, I can take away that charge. You see that? So if I take away that charge, then this sphere collapses there. If I charge it up again, there we go, I can repel it against the pull of gravity. And then ironically, there we go. It actually, it will actually stick to me. And I can't help that because I'm just naturally an attractive guy there, right? You see that? Okay? And all it is, what do the electrons like in my body? They like the what? They like the positive charge there. And eventually it just loses its charge there, okay? So at the end of class, I'll let you guys try this out. It just needs you guys to be really careful because this thing's pretty fragile, but also you can ruin like your phone or a computer or the projector and all that, okay?